today.
No, we're using to.
Is it that?
Yeah. Okay.
So, hi everyone. Sorry I'm a bit late. My name is Mikhail Sekachev. I work at the Joint Institute for Computational Sciences. And this HPC series topic is Introduction to Parallel Programming with MPI. And this is actually split into two parts. Today we'll talk about the basics of message passing interface, and we'll go into point-to-point communication. And we'll start talking about collective communication and MPI data type. So before I start talking about MPI, so what is computing? So it is defined as the use of multiple computers, processors, or cores that work together on a common task. And we say that each processor works on a section of a bigger problem, and we say that processors are allowed to exchange information with other processors. And that's where I come into play. So to illustrate the need for message passing interface, I decided to throw in this picture of good old PC cluster, where you can see a single core computer connected to a whiteboard, to other, and when the computers work in parallel on a common bigger task, they have to communicate. The API creates this layout for the programmer to be able to give instructions to processors so they can communicate with the network. So let's talk about message passing interface. So what is MPI? So in 19, the MPI forum that included approximately 40 organizations, including vendors, researchers, and library developers, they together and established an MPI specification. So what does it mean? Basically, before 1992, vendors had their own implementation of MPI, and it's basically a big mess because the codes were not. I mean, you could not port your code on different machines. Libraries were not standard. So when the MPI forum came up with the specification in 1992, everything became standard, and today's MPI specification basically effectively eliminated all of the previous implementations and MPI implementation. These MPI standards nowadays. So MPI is not a library, but rather specification of what type of library to see. So with standardization, we get syntax that is standardized. So MPI specifications propose an MPI syntax that everyone has to adhere to, and of course the functional behavior of MPI calls is standardized as well. So you can write a single MPI code and you can import it to machines and you can use different libraries. Now, as libraries are concerned, the most popular MPI implementations are MP and an MPI. There's also RAM and Cray machines that we have here at NICS and NICS. They come with Cray MPD, which is Cray ships their machines with, and it's based on MPD. General MPI program structure. So every program would include MPI include file. Of course, followed by whatever the in your program, and then code start. So the program really is part of serial code, and have to initialize it using a certain library or function call that I'll talk about later. So from within your serial code, you start your parallel code by initializing the MPI environment. Work and message passing calls, and then once your parallel section of the code is done, you terminate the MPI environment. And then go back to your serial code, then ends. So an example of the C serial code, or world code. So every program begins inside a function called new, and every function starts with an open curly bracket and ends with a closed curly bracket. And for those of you who program or knows how to program in Pascal, this would be equivalent to begin and end statements, if someone still remembers that. So from main, we can call other functions, including built-in functions such as printf that we have here, which basically prints a character string to the standard output or screen. Of course, the standard functions are defined somewhere, and that's what they include preserved directives for, which basically during the compilation process it adds additional code from header file called std.io, and that syntax is defined. So the basic C code and change it to be an MPI. As I add an include statement, include MPI.h. So we header file for the MPI library, and we have the MPI environment. So this was the MPI underscore init function called e4, and then we terminate our MPI environment, and that's what we use MPI finalize for. So your first MPI code. So we all now know how to program in parallel, so we can go home now, right? Not quite. So, but these three lines are the lines that we will use in every single program. So how does this work? Well, when you compile the code, you get a single executable. An executable is executed on a process. So you have to replace the analysis when you run it. So in this example, we run it on 4 processes. So we have process 0, 1, 2, 3. All of them execute the exact same executable, and all output the exact same result, because that's called from the code. Every core or every process will print hello world to the screen. So it's a program where you would just one hello world, you'll get 4 lines. API syntax. So the syntax is pretty simple. Well, of course, C names are case sensitive, and names are not case sensitive. So, every function name or in MPI library starts API underscore this. Now in C, MPI has to be capitalized as well as the first letter of the function call. So for instance, MPI underscore extend will have a F capitalized in C. In Fortran, you just have to have MPI underscore in case it's random. It's sensitive. The difference is that in C, of course, the errors are returned by the function. In Fortran, they return to an extra parameter that we specify, an extra argument in the function call. So that's pretty much it. Now, that MPI, the so-called SEMD programming paradigm, which stands for single core multiple data programming paradigm. What that means is that we run that same program on all of the processes process operates on different set of rules. So that's analyze the problem and solve it parallel. So this because we generally can say in if statements such as if my processor ID or my range ID equals certain number, then I do this part of the problem, do this part of work. And if my processor ID is some other number, then I do this part. You have to have some means of identifying the process, right? So we call range. So every process will have a range. So how do we do that? We process identify. So the first function call I have listed here is MPI range. And the function call determines the range of the calling process in the communicator. And so what that means is that this function call returns each process or processor ID. So the range starts at 0 and goes to n number and the process. So both C and Fortran. The Fortran starts at 1. The range it still starts at 0. So if there is 3 processes that you run your application on, then you have range 0, 1, and 2 for both C and Fortran. So you have to be careful with that. And in Fortran. MPI size is another process identifier function. Well, not process identifier. This function determines the size of the group associated with the communicator. Again, simple wording, it reviews the total number of processes that you run your application. Use word communicator a lot, so let me elaborate a little bit on that. So MPI uses objects called communicators to define collection of processes may communicate with each other. So when these messages, they have to be within the same communicator. It means they initialize the MPI environment that we've already seen in our first problem. It actually initializes a default communicator for you. It's called MPI world. And name suggests MPI world and all of the processes. And for speed, just use it whenever a communicator is required. And this is really true, especially when you begin programming. You would just initialize your MPI environment and use MPI world communicator whatever you need it. Don't worry about that too much. So now, use our knowledge. We've learned we learned 2 more function calls, MPI MPI cloud. Let's now program that instead of writing simple hello world statement, we'll something like hello from 3 of 4 or hello from 0 of 2 of 4. And of course, first number indicates the range of the processor that came up. And then 4 is the exact same number, which is the total processes, API communicator, and of course every process should that number. Now we don't want to write a code that will only run on 4 processes. We want to write a general code that will run on any number of processes. And here's the so just like the first problem, the first code we looked at, we enter file, MPI.h, we include that. Now we add 2 more, we declare 2 more integers, my range and number of new procs. My be that we use to store processor's range. Number of procs is the integer variable we will use to store the total number of procs. So we need MPI environment using MPI unit. And then this new function calls that we defend over MPI com rank, MPI com size, and see you have to specify the communicator, MPI com world, we just created using MPI init. Function return MPI com rank returns a rank for the processor and stores it in my rank, and then size the number is the number. And the process will execute the exact same instruction, printf below from, it will use my rank and numproc, which will effectively generate or whatever number of processors you have different result. So we would need, as opposed to the first problem where the result was the exactly same, it just said hello world 4 times. It wasn't really a parallel program. We had the exact same result. It didn't really take time. This program clearly indicates that we work with 4 different sets of data. Of course, it's a very basic program, but it indicates the very concept of parallel program. So what we just, I found wrong. Someone's controlling me. So the AI function calls just went over are, belong to class of API environment management. So we talked about API size, rank, and API finalize. Used for initializing, wiring, and terminating the API environment. Other management routines are MPI abort. You might want to use it with an error statement. If there is an error in one of the MPI function calls, you can abort MPI and stop your program. And other useful MPI environment management routines are get processor name and initialize MPI API time and management routines. Now, API basic data types for C are listed on this slide. So whenever you send a message or a message or doing kind of communication, you can't really use the original data types of, say, C or Fortran. So you have to, instead of using float, you would use MPI float, and D, of course, all of this has to be capitalized, and W use MPI double, and in Fortran, instead of real, use real. So about point-to-point communication. So API point-to-point communication is a process of message passing between two and only two different API types. So it's a collective communication, which we'll talk about two, where you can have multiple processes involved in communication. Here, we're talking about communication type where only two processes are involved in communication. So one is always performing extend operation, and the task is performing a match and receive operation. So there will always be a tension. The point in teams can be either blocking or non-blocking. In general, blocking calls stop the program until the message buffer is safe to use, and we'll talk about it in more detail. And non-blocking calls allow you to separate communication from communication. And of course, you find 4 communication modes for blocking and non-blocking calls. Well, and these are synchronous, waiting of that standard mode, and does not say communication mode, so it can be blocking or non-blocking. So basically, 8 types of send and I'm using so there's 8 types of send and 2 types of receive. Yeah, let me turn off the, you can record it, when I practiced earlier. Okay. All right. So what needs to happen in order for a communication to succeed? So first of all, sender must specify a destination range. So write a letter to your friend, you have to specify the address. You specify a valid source. So you know the receiver needs to know from where to expect the message. The data must be the same. So basically, you have to be on the same platform in order for UPS to be able to deliver the package. It must match, and each type must match. So needs to know that you are sending him a letter, not a package. In that regard, the receiver platform must be as well, and is that friend, your mailbox needs to be large enough. It needs to be prepared for the good package or let his mail. So let's write a program where process 0 sends a message to process 1, and process 1 receives it from process 0. They said the sending process to initialize the send operation, and at the same time, the receiving process needs to initialize the receive operation. So how do we do it? Here is a will do just that. We include the header file. Now know what INT my range is. We declare a variable that will be used to store process range. Then also initialize a header variable called mtag. We just do 100 to it. Any number as long as it's the integer size. After string message of characters is also declared, and we declare a status variable of type MPI status, which for our receive call, we can see it defines their own data type that is I'm sorry, your initial API environment, you assign the range by range, assign range randomly. You don't really know what process or what specifically what core is going to get what range. But it always starts with 0 and goes to n minus 1. Here's the program that MPI sends and receives. So let's rerun this program on using 2 processes. You can actually run the processes. For simplicity, I'm sorry, we'll just write on 2 processes. If my rank is 0, so if I'm process that 0, then I'll execute the first part of the if statement. So what I do is I initial message the hello world. So remember that it wasn't initialized. So process is actually declared it as message 12, but it was empty for both of them. Now the process with range 0 will initiate with hello world and it to process So how do we do this? We use MPI send. We specify the buffer, the send buffer, which is message. Again, the C program, so it's a pointer. We send 12 characters, so we have 12 MPI char. Not use the standard C data. We use MPI data, MPI char. You specify destination, which is 1, and tag, and tag. You specify the communicator, same tag on both communicators. Then process 0 will print some process, well, not some exactly, process 0, hello world. Process 0 counts hello world. So we know that the send operation succeeded and process 0 successfully send the if I'm rank 1, I skip the first part because my rank equals 0. So the else statement. So else if my rank is 1, I do the receive. And as you get, it's pretty much exactly as MPI send, specify the buffer of characters. You expect the message to arrive from processor 0. So that's where the handshake will be happening because of this, because if you correctly specify the location of the message on the receive side. So end tag, the same 100, MPI world, and you return a status. So let's do the check. So as I mentioned, in order for communication to succeed, sender must specify a valid destination range. So the sender specified 1, so that's good. Receiver must specify a valid source range. So they specify 0, so it expects a message from process 0. The communication is the same, so we are using the same default MPI called world communicator for both MPI send and MPI receive. Tags must match. We actually message type must match. So MPI char and the buffer must well exactly specify the buffer. So that's good. So that's good. Would input show them as well. The receive process 1 will output the exact same message as 1 world. So the receive doesn't succeed, then it will still be blank. So let's talk about blocking the non-blocking. So blocking stands for receive call, suspends execution of users until the message buffer is sent or received is safe to use. What does that mean? So basically, in case of a blocking stand, this data that you can send have been copied out of the send buffer, but data have not necessarily been received in the receiving tab. So the content of the send buffer can be modified without affecting the message that was sent. So the message can reside in the buffer, or you basically wait until the receive acknowledges that the send buffer is to be used. And blocking receive implies that the data in the receive buffer are valid. So you can suspend the execution, make sure that the receive operation succeeded. So this is an illustration of that process. So blocking and send and receive. Standard specify that the blocking send will receive the last return until the send buffer is being used or the receive buffer is ready. So in this schematic, we have two processes. We have send process and receive process. simultaneously. And so the user section indicates the computation part of the program. And then at some point in time, the send process starts sending the message. And since the block is send, it will suspend the execution of the send and wait until the receive operation receives the message, and then they both receive the running process, the runtime. So here is that there's an overhead on the send side because it has to wait until the receipt was ready, actually completed the message transfer. Non-blocking calls, they run immediately after initiating the communication. So in order to send buffer, the program checks for its status. And so we use a wait call, basically verifies that the send or receive buffer is safe to be used. So blocking or non-blocking send can be paired to a blocking or non-blocking receive. That, of course, makes sense. What you do. Blocking send and receive are the examples of non-blocking send and blocking receive. So with a non-blocking send, as I said, you initiate a non-blocking send and then continue. You move on and do some work. So that first line. So the takes time before it becomes ready, and once it's ready, it starts to receive the message that was sent, say process 0. And when complete, and the flip side needs to reuse the buffer, you have to make sure that you do the wait, make sure the send buffer is used. And same applies to non-blocking receive. So you can eliminate time on the receive side or send side by using non-blocking send. So the difference between blocking and non-blocking function calls. So as I said, I have 8 different types of send. So first of all, blocking and non-blocking, which we have talked about. Worlds for each of them. We have a standard, synchronous, buffered, and wait. But there's two receives for all of this. They're blocking or non-blocking. So send calls and 2 receive calls. What about the synchronous? So see, we started whether or not you actually post. So in this diagram, we have a separation that initializes the send with the arrow pointing down. So then this will complete successfully only if an action is people posted. And initialize at any time, you'll have to we still have to make sure the match receipt is posted. So that's the idea of MPI. Anyways, you have to have some hints. Task tells the receiver that the message is ready, and it waits the receiver's self-knowledge. So because of synchronization, we get synchronization overhead. We have to shake and wait until gets it from the send side. So handshake and wait. So this is the safest and most portable way of sending messages, but it's this is the slowest one, but at least the future. If MPI reset can only be matching with already posted. So, so it asks for the handshake. So it allows you to remove the handshake after you take that time, but you will make sure that you need to post your receipt. Otherwise, the operation runs on the phone. So completion of the send operation does not depend on the status of an action received. Or it just starts sending data, doesn't really care if the receiver is ready or not. So as you can see, you can minimize overhead by using the ready send, but you have to be careful using mode of the send is buffer send. Again, it can be started whether or not a matching receipt was posted. As opposed to the previous one, it may actually complete before a receipt is posted. So buffer, so you put your message into the buffer, and then you move on. So send operation is very, buffer send is safe operation because you put it to the buffer and then move on. However, one thing can happen, and that is you might run into where an insufficient buffer space is allocated. So you need to make that your messages fit into the buffer size, which is done through MPI environmental variables. So, different ways of doing send and receive, and US grammar has to get more special. And standards actually help you to avoid making those decisions by introducing a standard send, which, as implement an MPI specification requires is either synchronous or buffered, and up to the vendor to specify whether it is synchronous or buffered. So they just, they index to give good performance for most programs, whatever that means. The standard MPI send is very simple and easy. That's something that the beginner would use. And finally, blocking receive. As I said, we want to receive operation which can match any end nodes. So we have 4 different nodes, effectively 3 only, and there's only again, receive returns only after the receive buffer contains the newly received message. And unblocking receive can complete before the matching send has completed. Okay, so let's look at a problem that looked before, where process 0 sends it to process 1, and process 1 receives it from process 0. Now let's go a little bit so that it didn't work on a certain number of processes. Let's say we run it on using 1 core, 2 cores, 3 cores of processes and see what happens. So here's what I modify. Will this work if I run a single core? So I have only 1 process. So we can skip the first part of the cell. We already know what it's doing. Let's go to the body of it. So we run this code on a single core. So there's only 1 rank, only 1 process, and its rank is 0. My rank is 0. Of course, execute this part. Which is 0. I initialize the message with hello world. And send that message to where? Process. In yellow. Well, is there a process 1? No, in this code on a single core. is the rate from 0 to 0, not 0, 1, 2. Is fatal MPI sent invalid range stack. That exact error you would get by writing this code on a single core. Now, let's program using two processes. If my rank is 0, I go, and I give the if statement. My rank is 0, I initialize the hello world, and I execute AI send function, and I send it to process 1, which is the first valid statement. Process 1 does do this. And then I do the else part because I've already done the if part. I do MPI finalize, and everything is nice and square. I'm ranked 1. What I do? My rank is 0. That's correct. I skip the first part. I do else. And what I do is I receive the message, so I see that the message buffer is still 12 characters, so everything is nice. Same data type, and I expect a message to write from process 0 and match. I mean the same in the icon world, and the status is so I expect this program to work into that. And this is the output of that program if you run it on two processes. Process hello world, and process when it receives the message, it outputs the exact same hello world statement. Now if you run this code of 3 processes, process 0 completes the first part, else you don't do the else. Process 1, I don't part because my rank is not equal to 0. I do else part, so I receive a message from process 1. Well, did process 1 send me the message? Yes. It did. Well, what if I'm process 2? Because you're running it on 3 cores, so process 2 will do something as well. I'm 0, I'm not do the first part, and I want to do the receive part, and I have a message on process 0. This is 0 ever send me the message. I'm process 2. No, it runs one message to process 1. So what's process initiate block and receive operation using MPI receive, and it gets a message from process 0, which is and the typical deadlock situation. It's called the deadlock situation that you can run in by improperly using blocking or just improperly writing your code. Usually it's the blocking call that creates it by improper usage. The application would just sit there and wait and wait and wait. Even though this 1 and 2 seem to have no problem, process 3 will the whole calculation and this is and if you're not running it on big supercomputer, can waste thousands and thousands of hours. Sitting there and not doing work. So what if I do else? If I put explicitly the else part is only for N1, there can any number of processes. That is my one. Of course, some of you have already figured that out. So I think about it for this part for MPI concerns as well as point combination. Here are some for you to get more into. um, pages, of course, and a very good online page uh, um, source uh, of, I think the national and a very good set of MPI web pages are posted at Aragon's National Laboratory as well. A good set of exercises is available on their link. So you need to read it, and these slides will be posted on the web, so you'll all have access to this page. And at this point, I will stop and take questions. Is there any?